Hey everyone at UMS Engineering. So think about how a radar system works. It sends out a pulse and then measures how long it takes for the echo to come back, right? Well, that returned pulse is just a time-shifted copy of the original signal. And to figure out anything useful from it, like how far away an object is, engineers have to know exactly how to handle these transformed signals, how to shift them, stretch them, or even flip them around. This week, you're going to learn exactly how to do that. This explainer is designed to get you completely ready for week 2 of Signals and Systems.
So here's our game plan. We'll kick things off with the why, to connect all this math to the real world. Then we'll build up our toolkit piece by piece, starting with time shifting, then scaling, and reversal. Now, the real fun begins when we start combining these operations, so we'll walk through the proper way to do that, solve an example together, and then finish up with a quick checklist so you can walk into class feeling totally prepared.
Okay, let's dive right in. Before we even look at a single equation, it is so important to understand why we even do this. This isn't just some abstract math problem. It's actually the language we use to describe and build real engineering systems. And that radar example is just perfect. The signal that comes back to the radar is, for all intents and purposes, the same one it sent out, but it's been transformed. Specifically, it's been delayed. To get any meaning out of that, like the distance, you have to know how to work with that delay mathematically. Out in the real world, signals are getting shifted, stretched, and flipped all the time, and these tools are what let us make sense of it all. So let's grab our first tool from the toolkit, time shifting. This is all about sliding a signal left or right along the time axis, moving it forward or backward in time without changing its actual shape. And here's the math that makes it happen. For any signal, let's call it x of t, you can create a shifted version simply by replacing t with t minus t naught. That little t naught is just a number that tells you how much to shift. And it works exactly the same way for discrete time signals. We just use n and n naught instead. The direction of the shift really just comes down to the sign of that t naught value. If t naught is positive, we call it a delay, and the whole signal moves to the right on the graph. It happens later. If t naught is negative, we call that an advance, and the signal moves to the left, meaning it happens earlier. Okay, now this is the crucial part. I'm telling you, this trips students up every single year, so listen closely. When you see a minus sign inside those parentheses, like x of t minus 2, it means a shift to the right. I know, it feels backwards, but just think about it this way. For the thing to happen, the part inside the parentheses, t minus 2, has to be 0. And for that to be true, t has to be positive 2. The event now happens later, at t equals 2. So minus means right. Let's make this crystal clear with a really common signal, the unit step function, u of t, which you can see right here. As you can see, the basic unit step function is just 0 for all negative time, and then bam, at time equals 0, it jumps up to 1. Now watch what happens when we make a new signal, y of t equals u of t minus 2. That jump, that exact same event, has moved. The whole signal shifted 2 spots to the right. What used to happen at t equals 0 now happens at t equals 2. It's a perfect illustration of that sign rule.
All right, let's move on to our next couple of tools, scaling and reversal. Now, these don't just move the signal around. They actually change its shape on the time axis by compressing it, expanding it, or flipping it completely. So time scaling is where you multiply the time variable t by some constant, we'll call it a. And what this does is it either squishes the signal horizontally or stretches it out. It's kind of like hitting fast forward or slow motion on a video. And the key here is the size of that a value. If the absolute value of a is bigger than 1, say x of 2t, the signal gets compressed. It happens twice as fast and looks narrower on the graph. But if a is between 0 and 1, like x of 0.5t, the signal expands. It slows down and gets wider. And for any signals that repeat, if the original period was t naught, the new period is simply t naught divided by the absolute value of a. Now, for discrete time signals, scaling is a little different. The operation is called decimation, and it means we can only scale by an integer, m. What you're actually doing is keeping every mth sample and just throwing away all the ones in between. You can see how this is a huge deal. Unlike just stretching a continuous signal, you are literally losing data points forever. And our third tool is time reversal. This one's pretty simple. It just flips the signal like a mirror image around the vertical axis at time equals 0. Everything that was on the right side of the graph is now on the left, and everything that was on the left is now on the right.
If you think about it, it's really just a special case of scaling, where our factor A is exactly -1. Okay, so this is where it starts to get really interesting and frankly a bit more challenging. When you need to do more than one thing, like scaling and shifting a signal, there is a very specific procedure you have to follow. You have to get the order of operations right, or you will get the wrong answer. It's that important.
So here's that classic question. You see an expression like x of alpha t plus beta. What do you do first? Do you deal with the shift, that beta term, or do you handle the scaling, the alpha term? Let's clear this up once and for all and show you the professional way to do it.
Here it is, the foolproof method. I want you to burn this into your brain. Always, always factor the scaling term alpha out of the parentheses first. Just look at step 2. When you factor it out, you reveal the true shift. And here's the secret. The real shift isn't just beta. It's actually beta divided by alpha. So remember the sequence. Factor, then scale, then apply that true shift.
You know, theory is great, but there's nothing like actually doing it. So let's solidify this whole idea with a full worked example. We'll take it step by step, just like you would on your homework or an exam. Okay, here's our problem. We're starting with a nice, simple, rectangular pulse, x of t. It's got a height of 1, and it exists from time equals 0 to time equals 2. Our job is to sketch the transformed signal y of t, which is equal to x of 2t minus 4.
So, following our method, what's the very first thing we do? We factor. We look inside the parentheses and we pull out that scaling term, which is 2. This immediately rewrites our expression into x of 2 times t minus 2. And just like that, this new form tells us exactly what we need to do. A scaling by a factor of 2 and a shift of 2.
Right. On to step 2, scale. We're applying the scaling of 2 to our original pulse. Now, our original pulse started at 0 and ended at 2. How do we find the new boundaries? It's easy. We just divide the old boundaries by our scaling factor. So the start point, 0 divided by 2, is still 0. The end point, 2 divided by 2, is now 1. Our pulse just got compressed, and now it exists only on the interval from 0 to 1.
And finally, step 3. We apply that true shift that we found. The t minus 2 part tells us to shift everything to the right by 2 units. So we take our compressed pulse, which lives between 0 and 1, and we just add 2 to its boundaries. The start point at 0 moves to 0 plus 2, which is 2. The end point at 1 moves to 1 plus 2, which is 3. And there it is. Our final signal, properly scaled and shifted, now exists on the interval from 2 to 3. That's our answer.
And that's pretty much it. We've covered all the core tools for transforming signals in the time domain. So to wrap this up and to make sure you're feeling really confident for your lecture, let's just run through a quick checklist of the key skills you should have now. So before you walk into that week 2 class, ask yourself these 4 questions. Can you apply the sine rule for shifting without even thinking about it? Can you just look at a scaling factor and know instantly if it's compressing or expanding the signal? Can you take any signal and flip it using time reversal? And the big one, can you handle those combined operations using the scale then shift method we just practiced? If you can nod your head yes to all of these, you are in fantastic shape. Feel free to rewatch any part of this explainer if you need a quick refresher. Good luck with your studies.